So today's lecture will be, let me say, brief. We'll be talking about magnetic fields and magnetic forces of and on current carrying conductors. In other words, magnetic fields and magnetic forces of current carrying conductors and on current carrying conductors. We've spoken about charges. We've spoken about current flow. Excuse me. We've spoken about charges and current flow. We know that the rate at which charges move through a particular material is known as electric current. And we know in the last class, we spoke about a property of electric charges, which is that whenever they are in motion, they manifest magnetic properties. So that means that when current is flowing, which means when charges are in motion, they exhibit magnetic properties. And how do they exhibit magnetic properties? Magnetic field is created around them. So the figure we have here is showing a conductor in which current I is flowing in the direction of the arrow. And for the fact that current is flowing, it means electric charges are in motion. And since electric charges are in motion, based on what we spoke about in the last class, that means magnetic field will be set up around the conductor. And the direction of the magnetic field should be perpendicular to the direction of motion, just like we said in the last class. So in this case, this is the current carrying conductor. There is a rule which is known as the right-hand rule. It tells us that when you hold a current carrying conductor in the manner with which the hand in this diagram is showing, such that the direction of current flow and such that your thumb points in the direction of current flow, then the direction with which your other fingers on the right hand wraps around that conductor is the direction of the magnetic field. So the magnetic field in this case is around the conductor. So let's move ahead. So when we have two current carrying conductors that are next to each other, what happens? The current flow in the first conductor will create a magnetic field around it, and the electric current in the second conductor will also create electric force, magnetic force around it. So let's look at it in this way. In this is a conductor. This is another conductor. For the fact that current is flowing in this direction, we have magnetic field around this conductor. And for the fact that current is also flowing in the second conductor, we have magnetic field around it. And now it's like a scenario of having two magnets in the vicinity of each other. So when current is traveling in this direction and we apply the rule, the right thumb rule, we should expect that. Okay, let me try to see if I can draw something like that. Let's have a fresh screen, and let's say this is a conductor, and current I is traveling in this direction. we would expect the magnetic field to be around it. Let me undo that. Such that if my thumb should point in this direction, my fingers should point in this direction. If we have another current carrying conductor in the same vicinity with current traveling in the same direction, we would also expect magnetic field to be in similar direction. And this will cause, for the fact that this is having a magnetic field, the two wires are having magnetic field around them. And with the direction of this magnetic field, they are aligned, so they would experience force of attraction. And if the currents traveling, let's say we have another wire here. Let's take another wire, or let's take another conductor, another current carrying conductor. In this case, current I is traveling in opposite direction to that of the blue ones. We would expect the direction of the magnetic field to be opposite. If my thumb should point in this direction, if my thumb should point leftwards, holding this conductor, you should expect my other fingers to curl in this direction. And according to the right hand rule, that will mean that the direction of magnetic field will be in a direction that is opposite that of the blue ones, and that will, the force that will be created would oppose each other. So, and that will lead to repulsion. So, talking about magnetic fields of current carrying conductors. The magnetic field of an infinitely long wire can be obtained by applying Ampere's law, which is defined as this equation. Oh, sorry. Which is defined as this equation. B here is the magnetic field strength measured in Tesla, and it's the magnetic force exerted on the charged particle per unit coulomb magnetic force exerted on the charged particle per unit charge, which is in coulomb, per unit second. So that is per unit speed rather, which is will be seen very shortly. So Tesla, the relationship between Tesla and Gauss is that 1 Tesla is 10 raised to the power 4 Gauss, and the mu naught we have here is permeability of free space, and it's defined as 4 pi times 10 raised to the power minus 7 Tesla meter per ampere. So this is the expression that we'll be using, that I suggest you put somewhere in your memory. B 2 pi r equal to mu naught I. That is what I have enclosed. So this expression here is telling us that we have, when we are talking about an infinitely long straight wire, we have to cut the wire. Let's say the wire is of length L. We have to cut the wire into small fragments. When we cut the wires into small fragments, each of the fragments will be named as dl, and the magnetic field as a result of the small dl, the magnetic field as a result of small dl, when we sum them up together, it gives, that's why we have this expression here. So the magnetic field as a result of each of the small fragments of length will give us the total magnetic field. So talking about magnetic force on current carrying conductors. Magnetic force on current carrying conductors, I think we have seen this in our previous classes, that the magnetic force F subscript B Q is charge, V is velocity, and B is the magnetic field strength or magnetic field vector. And this operator here is cross product. It's not the normal multiplication or you have. So these are several scenarios. So now we have a current carrying conductor in the presence of magnetic field. And now we should imagine that this is a current carrying conductor and these are magnetic fields, and the direction of the magnetic field is such that it is pointing, the direction with which you are looking into your screen is the direction with which magnetic field is acting on the current carrying conductor. I should remember that the current carrying conductor, because it is carrying current, it should have its own magnetic field. So in this scenario, this is a current carrying conductor. In the presence of magnetic field, the current flow is zero. Since there is no current flow, it is not experiencing any force because it's in the, for the fact that it's in the magnetic field, since it's not carrying any current, then it will not respond to the external magnetic field, BIN. Let me go over that again. This is a current carrying conductor, and this is a magnetic field region. In short, magnetic field is beaming into your screen. Imagine magnetic field beaming into your screen, an external magnetic field, in that matter, BIN, beaming into your screen. The magnetic field is not affecting the current carrying conductor, all because the current carrying conductor is not affecting the conductor because the current flow is zero. The conductor is not carrying any current, so therefore the conductor is not having magnetic field surrounding it as a result of current flow. For the fact that current is zero, magnetic field created by current flow will be zero, and it will not respond to external magnetic fields. But this is another scenario where current begins to flow through the conductor. In this figure C, since current begins to flow through the conductor, then the conductor will have magnetic field surrounding it, just like we have said in the right hand rule. So as current is flowing through this conductor, we would expect magnetic field to circle around it, just like we've had before. So when it gets to the region where it is external magnetic field is applied, it will respond. Since it will respond, and the response will be as a result of magnetic force. And since it is experiencing magnetic force, it will bend in this manner. And now option figure D is another scenario where current is flowing in the opposite direction. And since current is flowing in the opposite direction, we would expect the magnetic field in this direction to have an opposite direction to what we have in figure C. And since magnetic field is a vector, we should not expect the direction of magnetic force of C and D to be the same. So because the current is flowing in opposite direction, the direction of magnetic field will be opposite. And if the same type of conductor flows into the same type of same conductor with the same current in the same magnetic field, but the only difference now is that the direction of current flow is opposite, then we would experience the magnetic force acting in the opposite direction like we had in figure C. If this magnetic field, current is flowing, if this magnetic field, the external magnetic field, BIN, if it is turned off, then it will return back to normal. It will look like what we have in B. If current is flowing, either flowing upwards or flowing downwards, and the external magnetic field is absent, if the external magnetic field is 0, then there will be nothing to interact with. The magnetic field generated by the conductor will have nothing to interact with, and there will be no bending. So let's move forward. So we can talk about current flow through a wire, and we should always remember that when we talk about current flow, we are still talking about motion of charges, the rate at which the charges flow through a particular cross section of wire. So in the figure we have here, a segment of current carrying wire in the magnetic field B. So now the magnetic field is still in the same direction, like you are looking into your screen. That is the direction with which the magnetic field, external magnetic field, BIN, is applied. So now, a segment of current carrying wire in a magnetic field B. The magnetic force exerted on each charge making up the current is, we've said this before, the magnetic force, FB, is equal to QV. Magnetic force is a vector quantity, velocity is a vector quantity, and the cross product of the magnetic field strength. And the net force of the segment of length L is IL cross B. When we try to define currents, originally we should say current I should be equal to the rate at which charges flow through a cross section. So something like Q over T. So, and that will mean that we can define charges to be product of current and time. That being said, we can redefine magnetic force to be I T V cross B. And now we have magnetic force to be product of current, time, velocity, which is a vector cross multiplied that is vector multiplication with another vector known as the magnetic field vector. And we should also remember that this is time, this is velocity. In my primary school, I was taught that velocity times time, or is it speed times time, is distance. And in this case, distance here can be said to be length. Then we can come here to say FB equal to I, which is current, product of time and velocity is length, and not just length, a length with a direction, cross B. So when we are talking about cross products, when we are talking about cross multiplication, that is not the cross multiply we have in maths, but when we are talking about vector cross products, the maximum is observed when the angle between the two items you are multiplying, this is the operator, when the two values, when they are perpendicular to each other, that is when you have the maximum value. And the maximum value you would have, will be FB, which is B, also a vector quantity, and will be perpendicular to both L and B. One minute, please. Okay. Sorry for the break. So just like we have this to be a valid expression, same is this. So when we have a scenario where we know the current flowing through a conductor for a certain length L, in the presence of a certain magnetic field B, in this case, B, can say BIN, then we can talk about the force that will act on that wire. Let me go over that again. This is a current carrying conductor. And current is flowing, or let's say charges are moving, or current is flowing. When current is flowing, when charges are in motion, we would expect magnetic field to be set up around the conductor. When the current carrying conductor is placed in an external magnetic field, the current carrying conductor will experience magnetic force, just like two magnets will experience magnetic force. When the current carrying conductor, we can describe it like a magnet. It has magnetic field. The magnetic field it has depends on the current that is flowing. But the major point I want to bring out here is that we have a current carrying conductor, magnetic field is set up around it so it can behave like a magnet. So when it is in the presence of another magnetic field, it will be as if it is in the presence of another magnet. So we should experience magnetic force, because now this is a magnet, and BIN, this small x is showing that magnetic field is being applied to this current carrying conductor in the direction with which you are facing the screen. And come to think of it, we've said this over and over again, the positive charge is flowing to the right. The external magnetic field is applied in the direction with which you are looking at the screen. That means that the direction of the magnetic field and this red line pointing to the right are perpendicular to each other. Then the resulting magnetic force is F subscript B, which is also pointing in a direction that is perpendicular to both the direction of charge flow and also the direction of magnetic field. So if the magnetic field applied, let's say the magnetic field applied, or let's say the current is flowing in a direction that is not perpendicular to the magnetic field, what we need to know is the components of that magnetic field that is perpendicular to the direction of current flow, or the components of the direction of current flow that is perpendicular to the magnetic field. And when we look at the founding definitions of cross product, when we say A cross B, A being a vector cross another B, is usually defined as A, the magnitude of A, magnitude of B, sine the angle between A and B. So when the angle between A and B is 90 degrees, that is A and B when they are perpendicular, that is when you have the maximum. That is when sine theta will be 1. When theta is not 90 degrees, then sine theta will be less than 1. And when A and B are in the same direction, when A and B are in the same direction, it will mean that the angle between A and B will be 0, and sine 0 is 0. So that means that, coming back to our expression that says the magnetic force is equal to Q V cross B, or I L cross B, when the direction of current flow, or when the direction of charge flow, when it is in the same direction of external magnetic field, BIN, FB will be 0. That is, instead of, if the current is flowing in this direction, I is flowing in this direction, then, and B is applied in this direction, FB will be equal to 0. So a wire segment of arbitrary shape carrying current I in a magnetic field B experiences magnetic force. The magnetic force on any segment ds, now I'm referring to this figure, the magnetic force on any segment ds is I ds cross B. And the magnetic force is directed out of the screen. In this case now, you can see that the direction of magnetic field is upward. Unlike in this scenario where the direction of magnetic field was inwards, in the direction with which you are looking into the screen. But now, in this case, the direction of magnetic field is upwards. The direction of current flow is, let's say, sideways. Then the direction of magnetic force will be mutually perpendicular to both upwards and sideways. And that will mean that it will point right at you. It will point out of the direction of magnetic force, will point out of your screen, pointing to you. And if the current flow is reversed, or if the direction of magnetic field is reversed, the direction of magnetic force will point inwards into the screen. So let's move forward. So now we have a straight horizontal length of copper wire having current 46 ampere. So we can write out the useful information. Current 46 ampere. Through it, what is the magnitude and direction of the minimum magnetic field needed to suspend the wire? That is, to balance the gravitational force on it. If the linear density, mass per unit length of the wire, is 42 grams per meter. So linear density, mass per unit length, (45.2 grams per meter. So the question is to say that magnetic force wants to balance gravitational force. Then we need to know the magnetic force, define our magnetic force, FB, to be equal to B, let me take it in vector. Magnetic force to be IL cross B. And we want to also use it to balance the gravitational force, Fg, which is M times G. So for Fg, it's as good as saying IL cross B equal to mg. And when we divide both sides by L, we should have mass over length times G equal to I times B. So let's try to define IL cross B. IL cross B should give us something like IL, let's say times B, sine theta, which should be the angle between the current, the angle between the current carrying conductor and the magnetic field, and that will be equal to mg. So the minimum magnetic field we need, the first condition is that the angle between that magnetic field and the wire must be 90 degrees. So when the angle between the magnetic field and the copper wire, when the angle between them is 90 degrees, that is when we can have the maximum force, and it will also amount to something like the minimum magnetic field required. So we assume that let theta equal to 90 degrees so that we'll have the maximum. So when we say theta is equal to 90 degrees, then we can say that ILB equal to mg. And we can say that B is equal to M over L G times 1 over I. So we know our M over L to be equal to 45.2 grams per meter. So we convert it to kilogram per meter for SI units. We know our current to be 46 ampere, and we know G to be 9.8 meter per second square, acceleration due to gravity. So with that, we obtain B. Some people are saying I should take it again in the chat box. Okay, let me try to see if I can take it again briefly. The question is saying, what are the magnitude and direction of the minimum magnetic field B? We've defined magnetic force to be equal to IL cross B, which I have defined to be IL, which I have defined to also mean that we can say FB to be equal to ILB sine theta. When sine theta is 1, then the value of magnetic field that will give you the same magnetic force will be referred to be the minimum magnetic field required to give you that particular force. When theta is, let's say, 45 degrees, you will need a higher magnetic force to give you a certain type of magnetic force you would have had if theta were to be 90 degrees. So when theta is 90 degrees, you will require smaller, or let me say, when theta is increasing, you'll be requiring smaller magnetic field to give you the same magnetic force. When theta is increasing, you'll be requiring smaller magnetic field to give you a certain magnetic force FB. So in this scenario, when theta is 90 degrees, when sine theta will be 1. So we can say that for the minimum magnetic field, we can say that ILB will balance up to the gravitational force. What is the gravitational force on the wire? It is mass times acceleration due to gravity. And when you make B subject of the formula, you should have something of this. B will be equal to mg divided by IL. And from mg equal to IL, we can get our M over L easily here, which has been provided as this. We can get our I, which has been provided as this. And we can use our G to be 9.8 meter per second square acceleration due to gravity. But you just need to convert this value from gram per meter, convert it to kilogram per meter. Then you have the solution. So I think we can move forward. So let's talk about torque on a current carrying coil. A current carrying conductor can experience a force that makes it to rotate when placed in a magnetic field. If a loop or wire is suspended in a magnetic field, the magnetic force produces a torque. Torque represented as tau, that tends to rotate the loop. The torque is responsible for the operation. The torque is responsible for the operation of a number of devices, including galvanometers and electric motors. I think we spoke about this in when we're talking about galvanometers, I think 2 classes ago. And torque, tau is defined as NAIB sine theta. Torque is a vector quantity as well. So this torque we have here is like the magnitude of the torque. And this sine theta is telling us that we should expect largest torque when the angle between the magnetic field applied and the current flow is perpendicular. When it's 90 degrees, that's when we should express maximum torque. And when current flow and magnetic field are in the same direction, where theta is 0 degrees, then we should expect 0 torque. Is the angle, so phi, yes, sorry, not theta, where phi is the angle between the normal of the plane of the coil and the magnetic field. N is the number of turns in the coil. So when you have large number of turns in a coil, you experience larger torque or loop of the, so the number of turns or loop gives is N, and A is the area of the loop, is the area of the loop, and I is the current flow through the loop, and B is the magnetic field strength of the strength of the magnetic field applied to the coil. So there is also what we call as the magnetic moment of the coil, which is defined as male coil, and is a product of N, A, and I. That is number of turns, the current flow, and the area. So we can say you should be able to bring this out from here. And say this is that torque B sine theta. Sorry, say you have to say torque is equal to moment, magnetic moment, product of cross product of magnetic moment and magnetic field vector. So let's move forward. So this is an example. We have a coil. We have a coil that has a rectangular shape. The coil has rectangular shape and current is flowing through the coil. We can see magnetic field applied to the coil. Current is flowing in this direction. And like we had in the previous slide, mu coil, which is the magnetic moment, is NIA, and torque, just like I said also, is cross product of the magnetic moment and the magnetic field vector. So we should experience large magnetic force in directions like this channel 2 and channel 4, where the current is perpendicular to the magnetic force B. We should experience large magnetic force there. But in scenarios where the current in this part 1, this is part 1, the direction of current is the same, the direction of current here. Let me turn my screen this way. One minute, please. Okay, so the direction of current in part 1 and part 3 is the same as the direction of magnetic field. The direction of B here and direction of I in part 1, they are the same. So the magnetic force we should experience there should be 0. The magnetic force should be 0 because the cross product between B and the length vector here will be 0. Since they have the same direction, the cross product will be 0. So there will be no magnetic force experienced on this part 1. But magnetic force will be experienced on part 2 and part 4. Although the magnetic force experienced in part 2 will be opposite the direction of the force you would experience in part 4. And that is even what we need. That is the torque we need. When the force that is applied on part 2 is opposite the force applied on part 4, then it should begin to turn around. It should begin to turn around in this axis. This should now be the axis in which when this is turning, when the force is pushing part 2 up, the same force will be pushing it down. So because the force is experiencing on part 2 is opposite the force is experiencing on part 4. So you should experience a torque, and the torque will be responsible for turning the loop about the magnetic field B. So looking from the side is what we have in the second figure, in which the loop is now turning around point 2 and point 4. So at point 2, it's experiencing an upward force. At point 4, it's experiencing a downward force. And that is what we need. And the product of the force applied to the center of the turning point is, we call the length here to the width of this rectangular coil loop to be B. Then the distance from this point to the center here will be B over 2. This will be B over 2. And that is why the torque we are experiencing here will be force and distance. That is not just any distance. Torque is product of the force and cross product anyway, cross product of the force and the distance between them. So unlike work done is usually defined as force times distance. This is dot products. This is scalar, where you multiply force and distance. They will give you a scalar quantity work. But for torque, is force cross distance. So it's a cross product. Torque is a vector quantity, while work is a scalar quantity. So the way we multiply them are different. So when we solve this F2, the current flowing through F2, the force on F2 is IAB. That is the current I times length A. Remember, this is length A. And the magnetic force B. And so doing that, we can, the angle between them is 90 degrees. So there is no need for any sin theta here. That's why we can say the product of the current I times length A times the magnetic force B, so magnetic field strength B. So we have this. And for the other part 4, we also have current I, product of current I with length A with magnetic field B. So multiplying this together, adding them together, we have I, A, B, B. And remember that the small letter A and small letter B, they are lengths of a rectangle, which we can multiply together to give us area of a rectangle. So A, which is area of a rectangle, is product of A and B. So coming here, the maximum torque we can have is what we have obtained as IAB. So the torque at every particular point in time depends on the angle theta between this coil and the magnetic field supplied. So the angle between B and the coil gives us sine theta is theta. The angle between the coil and the magnetic field supplied is theta. Therefore, the magnetic force will depend on that angle, and sine theta will be required to obtain the torque at any particular distance. So let's move forward. Our time is almost up. I thought it would be a short lecture, but this is another example. We should round off today's class. The example is saying that a rectangular coil of dimensions 5.4 centimeter and 8.5 centimeter consists of 25 tons of wire and carries current 15 milliampere. A 0.35 Tesla magnetic field is applied parallel to the plane. Calculate the magnitude of the magnetic dipole. Magnitude of magnetic dipole, that is mu coil, and it's equal to NIA. So, and that is equal to the number of turns times current times area. So this should give us the mu coil. And what is, so this should answer question A. What is the magnitude of the torque acting on the loop? Magnitude of the torque. Magnitude of the torque, that should be it says the magnetic field is supplied is parallel to the plane of the coils. If it is parallel, then I should expect our torque, which should be equal to mu coil cross B to be 0, because we need it to be perpendicular so that we would have a torque. So in short, whatever it is, this is the formula that relates the magnetic dipole moment, the magnetic field to torque. So if it is parallel, then there is no need to waste our time calculating anything. I think our time is almost up. Let me see. Okay, somebody is saying y b over a. So in the next class, we'll be looking at the concept of electromagnetic induction, electric motors, and electric generators. So, but before then, let us look at some questions that have been asked here. Saying why is it b over a? It is b over a because this is the axis, this is b, and this is b over a. B over a. Because the length, the width of the coil is b. That is why from the edge of the coil to the center of the coil will be b. So, okay, sorry, it's b over 2, not b over a. B over 2. B over 2. So I think I've answered that question. Why is torque not affecting line 1 and 3? Because lines 1 and 3 are parallel to the magnetic field. The direction of magnetic field and direction of parts 1 and 3 are parallel. So the cross product there will be 0. I thought torque is maximum when the field is parallel. No. Torque is maximum when you have the greatest force at angle 90, because torque is a cross product. So, unlike work is maximum when it is parallel. That is why work is product of force and distance in direction of the force. Yes, the answer is 0 because it is parallel. So it's 9 o'clock. See you on Thursday.